Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. For happy engineers, wherever you are. Now I want to share about the detention member design that was according into American Institute of Construction 2016, or AISC 2016. Let's enjoy this. We have three topics for discussing today in our civil engineering workshops about the steel truss tension member designs. They are structure analysis, structure modeling, and design and analysis. Before discussing about the structure analysis of the steel structure, we should know about the steel material. The steel material can be identified or can be classified from its strain stress curve. The strain stress curve can be found from the tension test that was performing by universal test machines. All about the procedure, all about the specimen of the tension test, we can see on American standard test material E8M for the metric units, or E8 for the European units. Okay, from the steel material we can find some parameters such as modulus of elasticity E, and the yielding stress Fy, and ultimate stress Fu. Of course, in the design of the steel structures, two parameters, the yield strength and the ultimate stress, is the most important, had been considered. Now we have a model of roof steel truss structure as shown as in the figure. The model had been built up by conducting the structure analysis applications such in sub 2000. We talk about the model letters. Now we want to talk about the definitions of truss structures. What is the truss structures? The truss structures had been divided as a member that was subjected by normal or axial load. What does it mean? It means another load had not allowed subjecting this member. We have the type loads of the normal or axial loads. There are tension load and compression loads. That's why we have three parameters for the truss structures element. What are they? They are A for the cross section of member, E for the modulus of elasticity of the member, and L for the length of the member. There are too many ways to find out the member load analysis. We have the joint analysis, the section method, the Cremona method, or furthermore we have the direct status methods can be used for evaluating, analyzing, calculating the member load analysis. The structure analysis applications such in sub 2000 can be used for more complicated steel truss structure system analysis. Of course, they have been run by numerical approach. They were called finite element analysis. We have three load types that was considered in the load analysis of the steel truss system structures. They are a dead load, leaf load, and the wind load. The dead load had been consisted of the self-weight, pure lens load, roof covering load, and connections. The leaf load had been divided as a human load that was stand on one of the nodes of the steel truss system structures. The wind load had been classified into the type of the wind load. There are the right wind and the left wind. When we analyze the wind load, particularly right wind, we had two types of the right wind load. There are the windward and the leeward. Conversely, the left wind had the leeward and the windward. The roof steel truss structure system had not been subjected by the load in partially. They work in simultaneous in load combinations. We had the type of load combinations that was accorded into two design methods. There are a level strength design, AISD, then we called the actual load combination, and the last is the load resistance factor design, or LRFD, then we call is the factor load combinations. For the tension member load design, we had to choose the largest axial tension load that was given by sub-1000 worksheets. Of course, the worksheet had considered the load combination and the load case analysis. The equation was given that the tension stress that was occurred in the cross sections of the member F is equal the tension load P divided the cross sections area of the member A, or in another form, the tension load is the stress or the tension stress multiplied the cross sections of the area. Hence, in the design, we can rewrite the equations in another form, that the nominal load or Pn should larger than the actual load Pe for allowable strength design ASD. In another hands, the nominal load Pn is larger than the ultimate load for load resistance factor design. Now we have the nominal tension load Pn is equal the tension stress multiply the cross sections area of the member A. When we get back into the design, particularly in the allowable strength design, the nominal load is equal the stress tensions multiplied the cross sections area of the member divided the omega. What is the omega? The omega is the reduction factor, for the yield criteria 1.67, and for the fracture criteria is 2. In another hand, for the load resistance factor design LRFD, we have the nominal load is theta multiplied the tension stress multiplied the cross sections area of the member. So what is theta? Theta is 0.9 for yield criteria as the reduction factor of the nominal tension load, and theta is a 0.75 for fracture criteria. The nominal load should larger than actual load for allowable strength design. In other hand, the nominal load is larger than the factor load for load resistance factor design. Well, from the previous sections, we know the tension member design had two criteria. There are yielding criteria and fracture criteria. The yielding criteria had not considered the presence of the bolt holes. So, in this case, we use the gross sections area AG for the equations. Okay. The AG or the gross section area can be found from a steel profile table such in an American Institutional Constructions, American National Standard Institutes, or anything steel international cuts others. For the fracture design criteria that's consider the bolt hole presence, we should calculate the effective area first. Okay, the effective area can be determined from or by multiplying the shear leg factor U by the net area. Okay, the effective area can be also calculated by multiplying the net area with some factors. Okay, here the factors usually determined by the engineering experience, maybe 0.75 or 0.85. Okay, then what's the net area? The net area had been defined or had been determined by multiplying the number of hole balls multiplied by the hole diameters and the thickness of the member. There are some references can be used maybe for strengthening your understanding in tension member designs with the specification for structural steel buildings, American Institute Steel Constructions 20M16, the minimum design notes for buildings and other structures by American Society Civil Engineering, and the Mr. Seeger's book, Steel Design, in the 5th editions. Finally, thank you very much for supporting NIPL project channel. We would like to serve you in structure analysis tutorial, finite element analysis tutorial, research partnerships, training and development in engineering paper, thesis, dissertation, design analysis, and forensic engineering consulting. Don't forget to subscribe this channel, like, and share. Thank you very much. See you. Assalamualaikum warahmatullahi wabarakatuh.